Welcome to my presentation. My name is Sang-ho Oh from Korea Institute of Ocean Science and Technology. I will talk about change of horizontal wave pressures on a caisson depending on the crest level of armor layers on the rubber-mounted core. The co-author of this talk is Mr. Jae-sung Lee from the same institute. In some cases, a number of concrete armor blocks are piled up in front of the caisson to reduce the impulsive wave loading on a caisson. This type of caisson is typically referred to as a horizontally composite breakwater. The horizontal wave pressure on such a caisson can be estimated by adjusting the modification factor lambda 1 of the well-known Goda's formula. In most cases, the crest level of the armor blocks is equal to or slightly higher than the crown of the caisson. Occasionally, however, the upright section of the caisson is not fully covered up to the crown level. For example, while construction is in progress or when the armor blocks are settled down or displaced after a repeated wave action. In such a case, the horizontal wave force on the structure can be larger than that on the solid caisson, but there exists no formula that considers such an effect. Another method of reducing wave loading on a caisson is to place the rubber stones in front of the caisson and cover them with armor blocks. Regarding this type of horizontally composite breakwater, there exist a few previous studies of estimating the wave pressure acting on the structure. So, we conducted experiments by changing the protection in front of the caisson and proposed a method for estimating horizontal wave pressure on the caisson. The experiments were carried out in a wave film of 50 meters long. Case models made of acrylic plates were placed at a distance of 28 meters from the wave pattern. Horizontal wave loading was measured by using pressure sensors, which were embedded into the center of each plate. This is the definition of physical parameters considered in this study. The experiments were conducted with 3 different case models. For the 3 case models, horizontal wave pressures on the caisson was measured with 4 different configurations of the armor blocks, which will be explained in the next slide. For each of the test case, 20 different regular waves were generated with the conditions shown in the table. Here, the case without any protection in front of the caisson is termed as T01. The case of full coverage of tetrapods and the rubber stones in front of the caisson up to the crest level of the caisson is termed as T11, which corresponds to 100% of coverage rate. The cases corresponding to coverage rate of 85% and 70% of the caisson are termed as T12 and T13 respectively. So a total of 12 different test cases were considered in the experiments in terms of the 3 geometrical parameters shown in the previous slide and the 4 configurations of the protection shown here. This is the photographs of the models. Tetrapods made of concrete with a nominal diameter of 7.5 centimeters were regularly placed in 2 layers, and the fall slope of the armor layers was 1 to 1.5 for all the models. This figure shows an example distribution of the measured wave pressure along the caisson according to the 4 different coverage rates. The wave pressure significantly reduced over the entire caisson when it was fully covered with tetrapods and rubber stones. When the caisson was partially covered, however, huge wave pressure acted on the exposed portion of the caisson. The peak pressure appeared at just above the crest level of the armored section. In this case, the highest pressure was observed at the top pressure sensor. In this case, the magnitude of pressure reached the maximum right above the still water level. Next, the upper figure shows a comparison of the 4 pressure distributions shown in the previous slide. Overall magnitude of the wave pressures becomes even larger when the caisson was partially covered than when the caisson was uncovered. Such a phenomenon was commonly observed for the rest of the test cases, as shown in another example of the lower figure where the result for a different wave condition is shown. Then the measured pressures were presented as a function of relative vertical position along the front wall of the caisson, or HP over HC. Here, HP refers to the vertical distance from the caisson bottom, and HC refers to the caisson height. So the value of HP over HC ranges from 0 to 1. In addition, the pressures measured with the protection in front of the caisson were normalized by the corresponding values with the same condition but without any protection of the caisson. Then all the data from the models can be plotted in a single figure like this. In the left figure, PT11 over PT01 is the horizontal wave pressure from T11 normalized by the pressures from T01. You can see most values of PT11 over PT01 are less than 1. This implies reduction of horizontal wave pressure by the protection with armor blocks. The black line shows the profile of mean value mu plus half of the standard deviation sigma of the data. Statistically, this curve means the upper 33% value of the data, which gives more conservative evaluation of the wave pressure compared to the average of the data. The rest two figures show a similar presentation of the data from T12 and T13 respectively. Here, the black dotted line correspond to the black lines in the previous slide, and the red line shows a fitted curve that gives a parameterization of the dotted line. These equations corresponds to the red line here. So values of PT11, T12, PT13 can be obtained by applying these equations to PT01 that can be easily obtained from Godot's formula. So it is possible to estimate distribution of horizontal pressure on the caisson covered with armor blocks on the rubber-mounted core depending on the coverage rates from 70 to 100%. The table here shows the mean values of the normalized wave pressure of the 4 zones. These values are presented in the figure on the left. Here, CR is the coverage rate and lambda C is the adjustment factor. Lambda C is basically equivalent to the values of the normalized pressures depending on the coverage rate. Then it is possible to draw fitted lines for each of the 4 zones that follow the data and to obtain simplified relationship between lambda C and CR based on the fitted lines, as suggested in the equation shown here. This is the last figure in this talk, which shows a comparison of the horizontal wave forces calculated by using the equation with the measurement. You can see there is very good agreement between the calculation and the measurement. Now let me conclude my talk. Analysis of the experimental data show that horizontal wave pressure on the caisson apparently increased when the caisson was not fully covered. This demonstrates the importance and necessity of full protection of the caisson up to the CREST level. Because imperfect protection may result in even greater wave loading than a simple solid caisson without any protection. Then we suggest a new formula based on parameterization of normalized vertical profiles of the measured horizontal pressure. For more details, please look at our paper, which has recently been published in Journal of Marine Science and Engineering this year. This is the end of my presentation. Thank you for your attention.